Okay, we're going to start today. So I've got actually a whole bunch of stuff that I want to get through today because I want to get through that whole reading 5.1, which was kind of long and kind of dense. Not actually very long, but kind of dense. So I want to cover all of that material today because really all of that is really about answering one question. And that question is what sets the strength of the H beta line in stars, which sounds like a really dumb and specific thing, but it turns out that encodes a lot of very subtle physics that we're going to talk about today. So, sorry, let me get my bearings. So, homework due Monday. I just put it up this morning. Sorry, I didn't give you quite a week, but it's not a super painful homework set. It's not as hard as the last one, I don't think. It's about the same number of questions, but I don't think the questions are nearly as hard. There aren't any prove this thing, and there aren't any weird ass integrals. It should be straightforward. Knock on wood. That being said, there'll be office hours on Thursday, and email me. I promise that I will check my mail on Sunday afternoon. If you have questions over the weekend, send me an email, and I'll try to fix it. Okay, so today what we're going to try to talk about is stellar spectra, and what I want to talk about are these spectra here. So, okay, there's always a long intro about the history of everything. Annie-Jump Cannon was a super, super influential astronomer for understanding all of these things. So what we want to understand is what sets the thickness of this line. So what is it that we're looking at here? And what are these numbers? Okay, HD stands for Henry Draper. And Henry Draper got his name on a catalog that Annie-Jump Cannon wrote. Because that's how things worked in the day. It's still how things work in the day to an extent. Like if you pay for it, then you get to put your name on it. But that's often not the people who actually do the work. That's a running theme in all of life, really. But anyway, we're trying to rectify that and recognize the people who did all the work, like Annie-Jump Cannon. So we want to understand what sets the width of this line. Okay, this one is H gamma. This H beta is here, which you can't really see in the projector. So let's talk about H gamma instead, because the physics is the same, just a slightly different transition. So we have these numbers. Okay, ignore the 9 and the 5. Just look at the O. The number and the Roman numeral are all slight modifiers to the big letter. Well, we'll worry about those later. Let's worry about the big letter first. So the big letter O, these are all B's. This is an A. And you can see that for the O star, this is a very weak, thin. It's not very wide and it's not very bright. Whereas for this one is a lot brighter and a lot wider. So what is it that we're actually looking at here? What is this thing that we're looking at? So this thing is a spectrum of the star. So what they do is they take a star, they make a yellow chalk. They make a diffraction grating, and they get a spectrum. Well, when I draw a spectrum, I draw it like this. I'm going to draw something that looks like that. That's not what this looks like. What this looks like is you took this light and you put it on a piece of photographic emulsion, so it gets dark where the photons are and light where the photons aren't. So what we're looking at here is this is a spectrum. All the black here is the brightness of the star, and then the light parts are the absorption lines where the photons don't hit the detector. So it looks kind of like this. You've got a lot of light and then some dark lines. Now they look bright because we're looking at a photographic negative, effectively. But so what is it that sets that? So they originally started classifying stars by the thickness of this line because, I don't know, sometimes you just got to try stuff. So they did that, and they sorted them by the thickness of this line, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. I think it's not P. But I know it goes all the way up to O. There's an O right there. So they sorted it based on the thickness of this line, but that actually doesn't make sense as a thing to look at. So what else can we look at? So we look at spectra this way, and here's a bunch more, F, G, K, and you can see that here these have a lot more lines. Why do they have more lines? Yeah, this one doesn't have very many lines at all. It's actually a complicated question that I'll get to by the end of the day. Why does this one have so many more lines? Why does this one have so many lines when the other one doesn't? Because all of the items in the other one are ionized, but they didn't know that yet. So we gotta walk through that. So I want to get to this picture here. Okay, so this is a spectra the way I would draw it on the board. So we have some flux, and we have wavelength, and you have a slope and a peak. I can't see the peak for this star because this only goes in the visual. So this is in wavelength in nanometers from about 400 nanometers to about 1,000 nanometers. This is what you can see. So I can't see the peak of this spectrum because it's in the ultraviolet, because the temperature of this star is very high. I know that now. So now that I understand things, I'm going to relook at these spectra and say, okay, I know that this one is the hottest because it's got this peak at the very in the very short wavelength. And I know that this one is cooler because I can see its peak. Actually, that's not its peak. This is the 4,000 angstrom break. This is because there's a whole bunch of crap in the way. There's a whole bunch of junk in the atmosphere, and it blocks all the photons. So there's a peak to this. So what we're looking at is a black body plus some absorption features. Does that make sense? The vending machine wouldn't vend me a Coke this morning. I don't know why. It just sat there staring at me. It wouldn't respond. And so I'm going to be dry mouth and panting all day. I apologize. So anyway, so we want to understand what sets the levels of these. So we understand what sets the peak. The peak is set by the temperature of the star, because the basic spectrum is a black body, and then on top of that we have an atmosphere that absorbs parts of that black body. So the basic black body is set by the temperature. What sets these lines? Let's talk about that. So, oops. Bear with me 1 second while I get my notes, because now I forget what the first thing was that I was going to talk about. No, I forget what the second thing was. That was the first thing. So we have this sorting, so that they sorted out after they set the chalk down and wandered off away from it. So we have this order of stars in order of temperature. O, B, A, F, G, K, M. And there's a really dumb mnemonic that goes with that that's really old and outdated and vaguely sexist. So I'm not going to use that one. But we need a mnemonic to come up with, to remember this order. So that's one of the homework questions, is come up with a cute mnemonic. Do you guys know what a mnemonic, does anybody not know what a mnemonic is? Raise your hand real quick and I'll explain it. So it's just a way to remember what these are, whatever that is. So only bugs are fascists. Get heights, man. Something like that, but make it make sense. Don't kill yourself on it, but you can see how quick you can do that, right? It's really dumb. So this is an order of mass and temperature. And these two things are related to each other in ways that we'll talk about when we get to stellar interiors. But so where do we get this color, and why do we have some of these lines that show up in some spectra and some that don't in others? So bear with me. Let me pull up my favorite spectra for this. Over here. Where am I? Here. So here, I like this one best. This is H beta. You can see as we increase temperature, there's no H beta absorption here. And then we get some H beta absorption, and then it goes away again. So what's going on? I'll give you the short answer. The short answer is we have levels. So here's a hydrogen atom. This is the ground state. This is the first level, the second level, the third level, et cetera, up to 0, where we have a free electron. So we have a whole bunch of atoms, and they all have a level structure like this. The hydrogen is easy to compute. We could do that. The rest of them are hard to compute, and I'm not going to make you do that. You'll take quantum mechanics and learn about all kinds of other crap for that. But anyway, they've got a level structure. The level structure is consistent and predictable if you have the right guns. So what sets which levels I'm going to be at? And what sets what photons I'm going to see. That's really the important thing. Or here, what photons are getting absorbed. So we've got the bright sun, it's, or the bright star, it's spitting off a bunch of photons. Some of them get absorbed. Why do they get absorbed? Because there's a thing there that can do some absorbing. Does that make sense? When is there a thing there that can do some absorbing? When I have electrons. So let's call this the hydrogen atom, and let's call this the ground state, the first state, and the second state. If I'm going to absorb an H beta photon, that means I need to make my hydrogen atom, the electron needs to jump from the 2 to the 3 level state. Does that make sense? So if I'm going to absorb a photon, my hydrogen atom is going to jump. The electron in my hydrogen atom is going to jump up to the next state, coincident with the energy of that photon. So if all of my photons are in the ground state, if all my electrons are in the ground state, and an H beta photon goes by, all my electrons are in the ground state, the H beta photon goes right past and is not absorbed. So I need to excite some of my electrons into this second state. How do I do that? Energy. What kind of energy? No, specific energy. One of the energies we've talked about. So there's thermal and kinetic, and they're really the same. So I've got thermal energy in the system, right? So I have thermal energy from my electrons rattling around, from my atoms rattling around. That thermal energy smacks atoms together and excites them. So in order to get any electrons in the first excited state, I need to have enough temperature to get there. And how much? I'll tell you in a second. So we have this process where down here it's too cold to excite any of that population. So we can't absorb this photon down here because it's too cold. There's no catcher for these photons. Nobody can catch these photons. And up here, what happened to the electrons? So as I raise the temperature, I get more and more electrons in this upper state. As I keep going, I get no more electrons in the upper state because they all become ionized. Once I take the electron off, then it's an ionized atom, and that's a different story. So I'll walk through this story a little bit slower again. Yeah, and I'm going to actually reclaim the rest of the board.
So really quick, just to clarify.
Yeah.
So the stars, like the type of star is on the left side. Right?
Yeah.
The top is just a bunch of photons.
No, that's an O star.
That's what?
That's an O star.
No, not the top of the left. I'm talking about the top. The x-axis, but on the top. Like, didn't you have on the last graph? You had a bunch of different lines labeled with.
Oh yeah.
Hydrogen something.
Yeah, let me pull up the last one. Where's my thing? There we go. And this one in
That.
this one.
Yeah. What's up top?
So this is wavelength. Is the horizontal axis is wavelength, and this one has the various lines labeled. So this one is H delta. This one is H epsilon. Here's H gamma. Here's helium-1 and helium. The first excited state of helium-1. I'm not sure what that is actually. So the marking is just marking the lines, but the wavelength is the horizontal axis. So this one is a longer wavelength than this one, and that's important because the wavelength is related to the energy.
Okay, and then what's the far right?
The far right is the designation of the star. So HD 3699 is a star in the HD catalog. So HD is the Henry Draper catalog. Annie Juncan had found a bunch of stars and did all their spectra, and they put them in this catalog. So this is just a star. It's a one particular star with its number. This one is Gamma Uma because it's the third star in this constellation. The rest of them don't have fancy names. Does that make sense for this graph? Yeah.
Just to make sure, so whenever you're jumping up like an energy level, you're absorbing a photon, and then
Yes.
as you go down, you're emitting one?
Yes.
Okay.
Key. That's a very key point. Yeah.
That's a bit of a tangent again,
Uh-huh.
but why do we not see photons interacting with the nucleus itself? Is it too small for the photon to interact with?
Energies again. So the nucleus doesn't care about anything that's as low energy as 13.6 electron volts. So if you want a photon nucleus interaction, it's got to be a very high energy photon to actually do any interacting. Yeah.
Is that what like photodisintegration is?
Of what?
Like the core of a star, like the light gets so energized that it's now interacting with the nucleus?
I'm not sure about that. Email me that and I'll look it up, but I don't have a good answer for you off the top of my head. Okay, so the first thing we got to talk about is the energy of the photons, or the energy of the atoms. So let's talk about the energy of the atoms. I am going to get some batteries for this so that I can stop climbing up on that thing every time. So, because I don't need the I don't need the projector for anything else. So. Okay, so we need to talk about energy. And we have two kinds of energy. We've got kinetic energy or thermal energy. Sometimes I separate the two, and sometimes I don't. Because thermal energy is just kinetic energy. It's just the energy of atoms knocking around. 1/2 mv squared. And the second one, we have electronic energy. And this is something on the order of minus 13.6 times n to the minus 2. So let's talk about this first one. And the first thing we need to do is talk about the distribution of the energy. So we want to talk about the distribution of kinetic energy. We talked a little bit about distributions on Friday. And there's some homeworks on distributions. So we talk about the Gaussian. So there's some homework games on Gaussians. The Gaussian is my favorite distribution because it shows up a lot and it's easy to work with and it answers most of your questions. It's not the only distribution. The other one we're going to talk about today is the Maxwellian. So how many atoms do I have with energy, with velocity between v and v plus some little element dv? Well, what I do is I assume that all of my motions are random of my atoms. And when two atoms interact, the new velocity is just the sum of the old velocities or thereabouts. I just add, when I want the velocity of this thing interacting, I'm going to add some stuff up. And so I have this random additive process where all the processes are identical, and this gives you a Gaussian. So the velocity for any one component of the velocity, let's say Vx, Vx is going to be distributed like a Gaussian, and a Gaussian has two properties. A Gaussian has a mean and a variance, and that's equal to some normalization, which I'm not going to write down because I don't care about it, e to the minus x minus mu squared over 2 sigma squared. So this is your standard Gaussian. It looks like e to the x squared with two caveats. One, we're going to shift x by some distance. All that does is move it left to right. And the other is we have some width, sigma. That's how wide the Gaussian is. So that's the variance of the distribution. So we know that each of my velocity components is distributed like e to the minus vx squared over some width, which happens to be 2kt. And then there's some normalization out in front. So this is f of Vx. F of Vx is a Gaussian. Does that make sense? So what does that mean? And it's centered at 0 because my cloud doesn't have any bulk motion. So we're thinking about, what I'm talking about is the velocity of the individual atoms in the atmosphere of my star. So most of them have 0 velocity, but then it falls off like that, like a Gaussian. It's got a mean of 0 and a width that's set by kT, the thermal energy of the gas. So the thermal energy of the gas is equal to 1/2 mv squared, and that's also equal to 3/2 kT. So this is the let me put it on, that's on here. This is for a typical velocity, but the actual velocity of an individual particle is not going to be this, it's going to be something random. It's going to be higher than that, or maybe in a different direction. Does that make sense? So this is a random quantity. Now when I take 3 Gaussians, I have, if I want the distribution of the total magnitude, how does V, the total magnitude, relate to my 3 components? V squared is Vx squared plus Vy squared plus Vz squared. Okay? That's just the vector norm. So one of these is distributed like a Gaussian, so when I add all 3 of them up and average, I get, I pick up an x squared from the volume element. So f of v is going to be e to the minus mv squared over 2kt times v squared times dv. So when the long story is longer than I want to say. It doesn't get me where I want, so I need to come up with a short story here to get from where I want to go. Bear with me 1 second. Let me back up and try that again. So f of v squared is the distribution of the total velocity of my atoms. Right? This is going to be equal to f of vx squared times f of vy squared times f of vz squared. For probability reasons. You just have to trust me on that one. Because they're all independent, the distribution of the total is just going to be the distribution of the products of the 3 things that make it up. Each one of these is a Gaussian. So I'm left with a Gaussian that looks like e to the minus vx squared times e to the minus vy squared, e to the minus vz squared. So I'm just multiplying 3 Gaussians together. When I multiply these powers together, this is just equal to e to the minus v total squared over the same thing, 2kt, the same denominator. But these are vector components, and I want to isotropize it, right? So if I want to actually ask how many molecules are in a particular region of phase space, I've got to do a volume integral, and when I do that, I pick up a v squared from the volume integrator. So the distribution of the distribution of Vx is a Gaussian. When I get Vx, Vy, and Vz, and I make the vector norm out of those 3 things, I'm left with a Maxwellian, which is v squared, e to the minus v squared over 2kt, which looks like this. It's positive always. My regular Maxwellian can be negative, but this is positive always. And it goes like that, and it has this long tail. So a Gaussian falls off pretty fast, but a Maxwellian, because of this v squared, has a long tail. So that means I have a whole bunch of extra stuff that's kind of going pretty fast. So I also need to normalize this to 0 to add up to 1. So f of v is going to equal some constants that I'm going to forget. So actually, let me write this the way I've been writing it. NV dv, this is the number of atoms with velocity v in a little window of dv, is equal to the total density times m over 2kt to the 3 halves times e to the minus m v squared over 2kt times 4 pi v squared dv. So the important bits are, this goes like e to the minus v squared, and there's a v squared out front, and the rest of these are constants. The other important bit is the kt, which sets the width of the distribution. So this tells me how many, the energy distribution. So if I want to know how many atoms have enough energy to ionize a hydrogen atom, what do I do? Well, first I need to, so let's say E, so I'm going to write this down as a probability. The probability that the energy is bigger than 13.6 eV. So that's what I'm going to ask. Now I don't have an equation, I don't have a distribution for the energy, I have a distribution for the velocity. So if E equals 13.6 eV, then V is 13.6 over the mass of the electron, square root of all that, and there's a 2 in there. Which is some number that's like a kilometer a second. The actual value I don't care too much about. It's the velocity that makes the energy 13.6 electron volts. Is everybody on board with that so far? So I want to know what fraction of atoms have a high enough velocity to ionize a hydrogen atom that they run into. So I've got all this velocity, 2 atoms run into each other. They're gonna, that kinetic energy goes into the electron energy. Sometimes there's enough energy to knock an electron off. How do I do that? So I integrate, so my distribution is here. So if I want to find the probability that the energy is larger than 13.6, I'm just going to integrate from, we're going to call this EI, from we're going to call this VI for ionization. So we're going to integrate from V ionization to infinity of this thing here, n of V dV, which is this integral. Graphically, this is what v squared e to the minus v looks like. Graphically, what we're doing is we're saying that, so this is the number of atoms, and this is a velocity. We're going to say we want to know what's the area under the curve above this ionization velocity. That'll give me the fraction of ionizing photons. Okay, so some of this bit with the exponentials may have not made sense. That's okay, I don't care too much about that part. The second bit about the number and the distribution, that I do care about. So this I want to make sure, if you don't understand what I'm saying here, just holler. So this gives me the fraction in a little bin, and I can integrate this over velocities to know what the fraction is in a large range. And I do that with an integral that looks like this. So if this doesn't make sense, let me know. Yeah.
Why does the range go to infinity if we only have like one specific velocity that we're looking for?
Because higher velocities work too.
Wouldn't the higher velocities create more ionized hydrogen?
Well, so if I have two hydrogen atoms, let's just pretend that I only have hydrogen. 2 hydrogen atoms, they hit each other with a rest velocity of 13.6 electron volts. They will, if it's exactly 13.6 electron volts, 1 electron will come off and they will come to a stop. For quantum mechanics reasons, that's not actually what happens, but let's run with it for now. If I have more energy than that, then an electron will come off and they'll bounce off with some recoil velocity. So I can take an electron off by hitting it really hard. The collisions here are not quantum mechanical. These are classical collisions. So unlike, and this is different from when we were over here. So when I was over here, to move from here to here, I need a photon with exactly 13.6 times 1 over 3 squared minus 1 over 2 squared. That's the energy difference between these two things. Only photons with that energy will work. Photons with higher energy might do that and then also leave you a residual energy, but probably will just go right past.
Oh, so anything with what we calculated their energy is over 13.6, that'll mean that we have no absorption lines?
No, I'm not talking about lines yet. Let's not think about lines. We're just thinking about who's ionized and who's not. We haven't gotten quite to the lines yet. So we're just thinking about who's ionized. So depending on the temperature, this line doesn't change, but if I drop the temperature, then I get something that looks more like this. And I have a lot fewer ionizing electrons, or ionizing collisions. Okay, is everybody comfortable with this? It looks like a Gaussian plus this v squared bit. The v squared bit comes from the 3 terms, if you care where the v squared bit comes from. And what it does is gives you a long tail.
What's that distribution called again?
This is a Maxwell-Boltzmann distribution. Oh, there are several 2-name distributions. This one's named after Maxwell, who invented light, and Boltzmann, who invented particles. That's not true. They didn't invent those things. Maxwell put together E and M and understand that. Oftentimes, this form is just called a Maxwellian. That's what I usually refer to it as. Okay, so now we know how many atoms I have at a certain energy. Let's talk about how many atoms with a certain kinetic energy. Let's talk about how many atoms I have with a certain electronic energy. And the electronic energy is quantized.
Sorry, before you
Yeah.
move on, the bottom graph, when you move the graph to the left, did you drop the temperature or increase the temperature?
That is a good question. That is the temperature going down.
Okay.
So less temperature means you have less hot electrons. So the tail goes down. That was a good question, thank you. So now I've got this sea of stuff. I've got all of this rattling around. I've got energies all over the place. I have this big distribution of energies. Some particles don't have very much energy, and some have a whole bunch of energy. These are all rattling around. How do I know how many electrons I have in a particular ionization state I? So I now is going to refer to which one of these levels my hydrogen atom is at. So I want to know the number that's at a population I relative to some other population J. Now I got to do it relative because there's not really a sense in doing things in an absolute sense because I don't know how many atoms I have. I don't know. So we're going to do everything relative. And this winds up making things confusing because sometimes I want the number of the second state to the number of the total. And this is one of the most confusingly written bits in the book where he just says, now we're going to combine these two things. Here's a weird, confusing equation that he doesn't really motivate very well. I'll come back to that in a second, but it's quite fun. So we only get the ratio of populations. And one of the most amazing things that Boltzmann did. So Boltzmann is one of the most important physicists, and he said that the ratio of two states. So this is like how many do I have in the ground state versus the fourth excited state, or how many do I have in the second excited state versus the third excited state, or whatever. So these are all ratios of different states. It's Gi over Gj times e to the minus ei minus ej over kt. And that's it. This is the thing that you just got to memorize. You can't derive this. There aren't a lot of those. There aren't a lot of things that you just have to memorize. Well, okay, you probably now just have to memorize. But some things you can't derive. Like I can derive the Maxwellian from very simple, basic things. Just, I've got two things that smash into each other. That's my initial ansatz, and then I do some math and I get the Maxwellian out of that. This I just have to hope that this is true, because we build all of StatMech on this.
What are G?
So I'll tell you in a second. So I and J are two different levels. G is called the degeneracy. And this is how many atoms you can cram into that state. So if you think about, how many of you have taken chemistry? How many of you have not taken chemistry, just so I get the compliment? How many of you kind of took a dodgy chemistry? All right. Yeah, I got a couple of dodgy chemistries. Okay, so one of the things that you learn in chemistry is all about electron orbitals, right? How many electrons can you have in one orbital? Two. Why? Spin. But why only two? Why not a million?
It's split into halves because it's quantized.
Because it's quantized and electrons hate each other. That's really the core, is electrons hate each other. So I can have one electron per state. And there's two states available, one for the up and one for the down. So in my electrons, what was that?
At least we don't phase through each other because of mutual electron hate.
That's right. So this is the number of electrons you can fit into a little bit of space. And electrons all hate each other, so they can't be in the same spot, but you can have a spin up and a spin down, and they count as different electrons. Okay? So if I've got a hydrogen atom, how many can I fit in my first electron? My first state, I get 2. In my second, I get 8. And it goes basically like n squared. Is 2 times n squared is the number of atoms I can cram into an orbital. So in the fourth orbital, I can cram, there are 16 states, and I get 2 electrons per state. No, 32 states, if I said 4. So there's 4 squared, which is 16, times 2 is 32, so there's 2 states. So this is the degeneracy. The other thing, no, I'm not going to talk about that yet. So let's talk about the second term. So this, you have to do some fancy stuff for that. The things for the electrons that you're going to need is free particle has G equals 1. There's only one way to be a free thing off in space. Hydrogen, Gi equals, let's call that Gn equals 2n squared. For more complicated things, you've got to do more complicated math, which I'm not set to do. You can learn that in quantum mechanics and StatMech. But these are the 2 G's that you should remember for now. Is a free particle has 1 and a hydrogen atom has 2n squared. And then the second term is actually the important bit. So this is just accounting. This is the energetics. This is where the physics is. E to the minus delta E over KT. KT is the thermal energy. 1/2 mv squared is the kinetic energy, and they're related. So KT is the thermal energy I have, and delta E is the energy difference between the two states. And this goes down like an exponential. So if I want to know what is the I population, this is just equal to the number of atoms I have in the ground state times e to the minus 13.6 times 1 over I squared minus 1 over 1 squared over KT. I make this an absolute value because the negative sign matters. This negative sign matters. You don't want to have this having a positive exponential because then everything explodes. So this is the Boltzmann equation. Okay, we've learned Maxwell, Boltzmann, And that's n of v dv equals e to the minus mv squared over kt times v squared times some numbers. And the Boltzmann distribution is ni over nj equals gi over gj e to the minus delta e over kt. So, if I want to find out, this is an example in the book that I'm just going to do without the numbers. Say I want to find out what the temperature is so that half the electrons are in the first excited state and half the electrons are in the ground state. Does that question make sense? Yeah.
Didn't you have a 2 kT on the bottom
Oh, yeah.
at some point?
Yes. That too is important.
Is it in both things, or?
No. Very important. This 2 is important for there's a 2 in the Gaussian, but not in Boltzmann.
Because of kinetic energy.
No, because of how a Gaussian works.
Okay.
You have a question?
So, yeah, because in the textbook, I'm pretty sure we were talking about this, and they were talking about probabilities.
Yes.
Now, so is that, what does that have to do with the degeneracy and all of that?
Which?
What?
For which?
For the Boltzmann thing. They were
Oh.
talking about probabilities.
Yeah. Probability is counting. So if I want the number of states relative to the other one, that's just the probability of being in that state. So I'm going to call this the number of the states, but I could really just as easily call this the probability of being in state I,
Okay.
because they're totally related. So that's a super good question that I have not really belabored too hard. That probability and counting are the same, and so you got to get your counting right, and then you get your probabilities right. So when I want to know how many are up here, that's like asking what the probability is. Do you have a question?
It's the number sum of the Maxwell.
Oh, it is some combination of the mass of the electrons and the kinetic energy. I can put it here if you want. It is m over 2kt squared to that. And that's all it is. But I want to draw your attention to the important bits. The number out front is important for getting the accounting right, but for the physics, the v squared up here and the v squared out here are the important pieces, and the kt. Okay, so if I want to, but my concept of time is not great, as
I
is
so understand.
as is common for the neurodivergent. But anyway, I only got 2 minutes to do what I wanted to do. Crap. Okay, so go through the probability exercise of half the population is in the first excited state. It's in the text. That one should make sense. I'm going to go through the second part. So I'm going to jump past that, and I'm going to go through the second thing, because we need to do the rest of the accounting, because where's my electron going to go? So if I'm really cold, all my electrons are in the ground state, right? Because of this. If t is a very, very small number, then this is huge, and this becomes e to the minus huge, which is basically 0. So if my temperature is 0, all my stuff is in the ground state. As I increase the temperature, things start to get excited and jump up into the first excited state. But they don't stop there, because I have this long tail on my Maxwellian. My Maxwellian, this is classical. This formally goes out to infinity. Now, realistically, that doesn't make any sense because it's relativistic, but we do it anyway. There's a fix for relativistic gas that we throw in later. But the tail is very large, so as I raise the temperature really any at all, some electrons are going to start to come off because I'm going to have really high rare collisions that are going to knock electrons off. So the Saha equation is like the Boltzmann equation, but we take the lid off. So instead of saying what's the relationship between one state and another state, we ask about the probability of being in one state versus totally gone. So how do we do that? I'm going to do that equation. So the book does it in a way that I don't like, because the book introduces the partition function, doesn't motivate it, and just leaves you with the partition function, which is like giving a 5-year-old a lathe Like, not that you're 5-year-olds, I didn't mean it that way. But it's a really huge tool that he doesn't use and doesn't explain how to use. You don't really need it here. I'll explain the partition function later. I'm going to show you how to derive Saha equations super fast. Okay, so Ni over Nj, we're going to start with the Boltzmann that we just started with, is Gi over Gj e to the minus delta E over Kt. Okay, so now I'm going to start talking about an electron that's bound. That's one of my states, and my other state is a free electron. So how many options do I have for my free electron? What are the energetics that are available? So this free electron has an energy that's equal to the ionization potential. So that's how much energy it takes to take it off, plus 1/2 mv squared, or p squared over 2m. This is kinetic energy, p squared over 2m. Think about that for a second. That's the same as 1/2 mv squared, but we're going to do it that way because we like momentum once you get to quantum mechanics. So this is the energy, and what I need to do is not, this is for 2 states. Now I need to say a whole bunch of states, so I have to throw an integral in here. So now I've got to integrate over all of the possible places that I could be. So I need to integrate over all of the possible momenta that I could have. And momentum's a 3-dimensional quantity, so this is now going to turn into chi squared plus p squared over 2m. So that's the upstairs in my thing now. And then I get a 4 pi p squared dp. So this is a volume and momentum space. What does that mean? Well, momentum space is just a 3-dimensional space with momentum, with axes px, py, pz, and I make a little cube in that. Yeah.
Is that chi plus p squared over 2m, that's the change in energy, or just the energy?
That's the energy of the free electron
Energy for,
from the ground relative to the ground state.
okay, and you just put it in for delta E.
Yeah.
So that's,
Because I'm just integrating. So what I need to integrate is all of the rest of the space. So this is all of the endpoints. And I need another thing. I need to know how many electrons I can fit per volume of phase space. So how many of you have heard of phase space? How many of you are comfortable with phase? How many of you have never heard of phase space, and what the hell is that? All right. So phase space that's entirely what I expected. I just wanted to make sure that I wasn't going to explain something that you just had explained to you. Phase space, so real space is X. And this is three-dimensional. Phase space is XP, and it's 6-dimensional. So you just make a vector. 3 of the elements are your position and 3 of the elements are your momentum. So now you have a 6-dimensional space. That make sense? That is phase space. So now I'm talking about all the possible configurations that I could have. And how big is a volume element of space? A volume element of phase space is h cubed. This is the quanta of phase space. It is like a little delta x cubed times a little delta p cubed. Okay, what's delta x delta p? We did this real quick at the end of Friday. That's Heisenberg's uncertainty principle. Because the uncertainty on x and the uncertainty on p, you multiply those together, that has to be bigger than some number. I'm going to talk about what is the smallest volume that I can have in phase space. Delta x cubed times delta p cubed is h cubed. So the smallest quanta of space that makes sense to talk about is h cubed. So I need to get that into here as well, and then I'm out of time. I'm going to pick that up in a second. But before I finish, I'm going to finish this math and do it again on Friday. And I'll go over the HR diagram. HR diagram doesn't take a ton of time. This takes a bunch of time if you want to do it properly. The important bit, here's what I want to get to, is if I want to look at the number in the second excited state relative to the number total, this is going to be my Balmer line. So this is how many are up here to absorb my Balmer photons relative to the total. I'm going to do this, and I'm going to do a little bit of math that I'll do again on Friday, and I get something, as a function of temperature, I get something that looks like this. I get this peaky function, where down here, I don't have any because nothing's excited. It goes up because I excite them into the upper state, and then it goes back down again because I start to ionize them. They're not there anymore. I can relate this to the strength of the Balmer lines in my spectra. So an O star is up here, a B star is here, an A star is here, an F star is here, G, K. So now I've got my stars laid out, and this is now not the number of Balmer of atoms, but it's the strength of the line, but those two things are entirely related to each other. I get an absorption line because I have atoms here. I'm going to stop there. I made it, but not necessarily in a coherent way. So I'll pick up all of the bits that I didn't do very well, and we'll talk on Friday. If there's a reading on, I think that there's nothing due Friday right now, right?
Homework.
Homework should be due Monday.
I homework you Monday.
The homework should be due Sunday, and there should be nothing due Friday. So if there is, don't do anything for Friday.